This is the binomial theorem. Remember, a binomial is a two-term polynomial, and a theorem just means that it's something that is proven, and so it won't always work. So what we're going to learn how to do is take a binomial and expand it without having to multiply it out all the way, or even with two variables in it. Instead of multiplying that out all the way, we're going to use Pascal's triangle, and I will show you what that is if you haven't seen that before. But we're going to expand a binomial, which means do the multiplying using Pascal's triangle. And we're going to calculate binomial coefficients, partly by using Pascal's triangle, and then a couple other steps. We're going to expand a binomial using the binomial theorem. We're not going to do any factoring. But let me first show you what Pascal's triangle is. Pascal was a mathematician, an astronomer, a philosopher. He was a brilliant man, but he discovered this triangle that looks like this. And as I'm making it, see if you can figure out where I'm getting these numbers from. There are a lot of patterns in this triangle, but we're going to use it to calculate binomial coefficients. So where do you think I'm getting these numbers from? And we can keep going as many rows as we need to, but okay, if you haven't noticed, each one of these hexagons is the sum of the two above it. Well, this one doesn't have anything above it, so it's just the sum of that one. But this one is the sum of those two. And this one is the sum of those two. So if you look at a binomial, like x plus 1 to the 0, anything to the 0 power is 1, isn't it? But x plus 1 to the 1 is x plus 1, or I'm going to say 1x plus 1. And x plus 1 squared is x squared plus 2x plus 1. X plus 1 cubed is x squared plus 3x squared plus 3x plus 1. And I could continue doing this without actually multiplying it. If you notice, my coefficients are from Pascal's triangle. Look, so this is called the 0th row. And this is the first row, and this is the second row. And notice that the third row has the 1 and 3, and the fourth row has the 1 and 4. But so the 0th row has the 1. X plus 1 to the 1 has a 1 and a 1. X plus 1 squared has a 1, 2, and a 1. X plus 1 cubed has a 1, 3, 3, 1. So that's how we're going to use Pascal's triangle. But I want you to notice every row is symmetric. See, 1, 4, and then it ends with 4 and 1. And then you just need to find the 6 in the middle. But look at this, 1, 5, 10, 10, 5, 1. 1, 6, 15, 15, 6. See how they're symmetric down the middle here like that, okay? So this just shows what I just explained to you. And this is with x plus y. But I want you to look at the exponents on here. But this is really x1, y0 plus x0, y1. And I'll show you why I'm writing it this way in a second. X squared y0 plus 2x1 y1 plus 2x0 y squared. Because we don't normally, y to the 0 is 1, and that's why it's just x squared. But I want you to look at the coefficients here with the x, 2, 1, 0. And then the y is 0, 1, 2. See that? So it expands up and it expands down. So I'm going to show you these patterns, and that's how we're going to use Pascal's triangle to do the binomial theorem.